My name is Cole Brower, and I'm a PhD student with the IDEA Lab at Arizona State University. Our work focuses on low cost robotics for education, in particular, laminate robotics and 3D printing. My work in particular focuses on the automated design and process planning for creating 3D printed multi material structures. In this presentation, I will be discussing the Voxelfuse modeling framework that we have developed, and my recent work on expanding this framework with features for generating structures with graded properties. Multi-material fabrication is a fabrication approach that allows for monolithic components which are comprised of multiple distinct materials. This allows mechanisms to be integrated into single components. For example, you could have joints or grips using integrated soft materials within a rigid body. This allows for robust parts that require minimal assembly. Although parts of this nature are typically accomplished using multiple processes, such as milling a part and then casting in the soft rubber materials, some additive manufacturing techniques can directly create multi-material components, such as polyjet 3D printing processes or multi-head FDM 3D printing processes. With multi-material manufacturing, there's also the potential for creating parts with graded mechanical properties. This can be achieved through a continuous change in material or structural properties as opposed to having a distinct boundary between materials. However, there are several challenges for multi-material fabrication. Currently, it is not well supported by CAD software. Most common CAD softwares today are predominantly built for geometry operations and creating assemblies, and these operations are generally not material aware beyond assigning specific materials to individual parts. Also, although many graded structures can be relatively easy to generate, they're often difficult to design manually due to the presence of high material counts or surface complexity. And often specialized algorithm implementations are needed for individual projects. The goal of our work is to create a CAD framework designed for creating and modifying multi-material structures. This framework is built around a model which supports multiple materials and material mixing, and all operations are material aware. This paper focuses on the generation of algorithm-based structures. We focus on three structures in particular: a lattice structure, a Tripoli periodic surface, and a dithered structure, all of which have applications in graded materials. This work also enables future work on the automated composition of graded multi-material structures by providing a single tool integrating multi-material design, simulation, and process planning, by enabling automatic processing of classes of parts, and by reducing the need for developing specialized algorithm implementations for individual projects. In our prior work, we have introduced the Voxelfuse Framework, which is a framework for working with 3D models in a material-aware manner. It uses a voxel-based model representation that supports material mixing by storing the material data in multiple channels similar to how a color image is stored. It includes methods for performing material-aware solid geometry operations, such as Boolean operations, material-wise addition-subtraction, dilate and erode operations, and Gaussian blurring. Some examples of these are shown in the figure on the right. It also includes algorithms to aid in the computation of manufacturing sequences. This framework has been implemented as an open-source, script-based software tool to allow it to be easily used in other projects. After completing these features for modifying existing geometry, the next step was adding features to generate new geometries. In particular, we were interested in structures that could be used to achieve graded mechanical properties using only two discrete materials. The first step was the addition of functionality for the generation of basic primitive solids. These play a role in building new model components or for defining volumes to select different model regions. The generation of primitive solids was implemented within our framework as functions which define a region that encompasses a model, then goes through each voxel in the model and checks if it is within the target shape. For example, to generate a sphere, the function would generate a cubic region and then compare the coordinates of each voxel in that region to the target radius for the sphere. After adding this basic functionality, our first main structure of interest is a lattice structure. This is a method of building a structure using a repeating tileable element. This provides a method for creating a single material structure that has varying density or graded properties by varying the element size or member thickness of these tiled elements. It also has the potential for use as a graded material transition, since you can combine a graded lattice structure with its negative to get two interlocking components. The creation of lattice structures was implemented in our framework by taking a user-defined template element and patterning it over an area, then intersecting the result with the target volume. So in the example on the right, you can see the template element in yellow, the target volume as the cylinder in the center, and then the result of tiling this element and intersecting with a cylinder on the right. This is an example of a uniform lattice structure. To create a graded lattice structure, we first take a model and divide it into a grid of lattice element locations. We then create a series of lattice elements with varying member thickness based on the composition of material in each of these grid areas. We then use an intersection operation to trim this set of lattice elements to the shape of the original model. Finally, we find the negative of the model to get the model for the secondary material. Another structure that can be used in a manner similar to a lattice structure is the Tripoli periodic surface. This is a surface which is defined by a function that is periodic in 3 dimensions, and it can be used to fill a volume with varying density or graded properties by varying the thickness of the surface or the period of the function. It also can be used to define 2 interlocking volumes by finding the regions that are above and below the surface. Because we are working with voxels at set coordinate increments, we implement this function by evaluating the function at each voxel and classifying it as either above or below the surface. If we would like to find the surface itself, we can then take the 2 resulting volumes, dilate them, and find the intersection. As with the lattice structure, graded properties can be achieved by dilating or eroding portions of the structure. The third type of structure we are interested in is a dithered structure. Dithering represents a method for simplifying a blur, which represents a true continuous material distribution, into a structure with a small number of discrete material types. Dithering is achieved using an error diffusion algorithm similar to image processing, but using a 3D diffusion filter instead of the 2D filter used for images. For our work, we use a 3D extension of a Stucky filter. This filter is used in particular because it exhibits uniform distribution in Z with no repeating artifacts. Next, I will present 2 case studies to show how the framework can be used for design tasks with multi-material structures. First, I will look at infill generation. Infill is a common practice in 3D printing, but slicing software typically treats infill and surface as the same material. If you had an application where you wanted to generate infill in a material-aware manner, such as if you wanted separate surface and mechanical properties, you could easily implement an algorithm with Voxelfuse operations to modify your model to fit this criteria. This script could then be used with other input models to generate other models of the same class. The code shown here illustrates using the Voxelfuse framework to generate the target volume, generate the infill structure, find the hollow and shell regions of the model, then combine all of these features to form the final multi-material model. Our second case study looks at the generation of a dithered material transition. This is a method for creating a material transition with graded properties using only 2 discrete materials. We implement this by applying a Gaussian blur to the boundary between materials, then simplifying the result with a dithering algorithm. The resulting operation can easily be applied to any model geometry or to an entire model. This code shows the steps we take to import a user-designed model, apply the blurring algorithm, apply the dithering algorithm, and then export the end result. Here, the top image is an additional example of applying the same code to a different model. The bottom image shows the result of applying dithering to a model that contains 2 materials mixed in a 7:3 ratio. Currently, our library is implemented for single-threaded processing. Since the performance is primarily dependent on voxel count, it will experience approximately cubic increase in requirements with increase in linear model size or resolution. To generate these graphs, we started by generating a sphere of diameter 10, which is a typical operation in a small model size. We then ran this operation at increasing scales up to 500 voxel diameter. Our future work on this project will perform a comparison of different types of graded material transitions. We plan to assess the performance of a range of graded material transition types and provide guidance on when to use each of these techniques. We are also investigating the use of Voxelfuse to design structures using materials which support tunable properties or active control, such as hydrogels. In conclusion, Voxelfuse provides an easy-to-use framework for designing multi-material structures with graded properties. Our presented case studies illustrate its application and ease of use, and our framework makes the design of multi-material structures more accessible. This work serves as a foundation for material-aware design automation. More information on this work can be found in our paper, Automated Generation of Multi-Material Structures Using the Voxelfuse Framework, which is available through the ACM Digital Library. The Voxelfuse library and all code presented in this presentation are available at the Voxelfuse GitHub repository. This work was supported through a grant from the Office of Naval Research.